What happens the moment a spacecraft leaves our sun's protection forever and enters a place no human instrument has ever touched? Before we answer that, hit that like button right now, hit subscribe, and tag one friend who loves space, because what you're about to hear rewrote what scientists thought they knew about the edge of everything. On November 5th, 2018, a machine built in the 1970s did something almost impossible to imagine. It crossed a line 11 billion miles from home, a line that separates our sun's territory from the rest of the galaxy. On one side of that line was everything familiar: the solar wind, the sun's magnetic field, the gentle push of charged particles that our planet has lived inside for its entire existence. On the other side was something else entirely: cold, ancient, untouched space that belongs not to our star, but to the galaxy itself. The spacecraft was called Voyager 2, and what it found on the far side of that line did not match what scientists had spent decades predicting. It was so different, so unexpected, that 5 separate scientific teams needed 5 separate research papers, all published on the very same day, just to explain it properly. This is not some spooky, unsolved mystery. It's the opposite. It's a story about brilliant scientists building their best theories for 40 years, sending a tiny machine to test those theories and discovering that reality was stranger and more important than anyone had guessed. And the strangest part is this: what Voyager 2 found out there in the dark does not just matter for astronomers. It connects directly back to the invisible shield protecting life on Earth right now. Let's start where this story really begins, because to understand what makes this crossing so remarkable, you need to understand what the edge of the solar system actually is. Most of us grew up thinking the solar system ends somewhere past Pluto. That's a fair guess. Pluto used to be called the 9th planet, and old diagrams of the solar system usually stop right around there. But Pluto isn't the edge, not even close. Pluto sits well inside a massive bubble that our sun creates, and inside that bubble, the sun is still very much in charge. Here's what most people never learn in school. Our sun isn't just a ball of light sitting quietly in the sky. It's constantly blasting out a stream of charged particles, called the solar wind. This wind rushes outward at hundreds of kilometers every second, and it pushes against the empty space around it like an invisible fist. Over billions of years, that pushing has carved out an enormous protective bubble around our entire solar system. Scientists call this bubble the heliosphere. Everything inside the heliosphere, every planet, every moon, every asteroid, every comet, lives inside the sun's zone of influence. But eventually, the solar wind runs out of strength. It thins out the farther it travels, and at some point far beyond the orbits of the planets, it finally meets resistance. It runs into the interstellar medium, the ancient plasma that fills the space between stars. Where these two forces meet and the solar wind finally loses the fight, that boundary is called the heliopause. Crossing the heliopause means leaving the sun's bubble completely. It means stepping out of everything our star has ever touched and stepping into the wider galaxy. This is the true edge of our solar system. Not Pluto, not the asteroid belt, but this invisible wall built from pressure and plasma, sitting roughly 120 times farther from the sun than Earth is. Reaching that wall took Voyager 2 41 years. Think about that for a second. The spacecraft launched in August 1977, back when disco was still playing on the radio and nobody had a home computer. It flew past Jupiter in 1979, past Saturn in 1981, past Uranus in 1986, and past Neptune in 1989. It is still, to this day, the only spacecraft in human history to have visited all 4 of those outer giant planets up close. After Neptune, most people assumed its big discoveries were behind it. Instead, its most important discovery was still decades away. Along the way, both Voyager spacecraft carried something unusual for a scientific mission: a golden record bolted to their sides, packed with sounds and images from Earth. Whale songs, greetings in dozens of languages, music from around the world, a message built in case something out there, someday, somehow, found it and wondered who sent it. Nobody expected the record to ever be needed for its intended purpose. It was almost a symbolic gesture, a small piece of humanity riding along on a mission built to study planets. Nobody in 1977 imagined that these 2 small machines would still be working, still transmitting, still teaching us new things about the universe more than 4 decades later. Yet here we are. For the next 30 years, Voyager 2 just kept going, slowing down slightly because of the sun's gravity, but never stopping, cruising through the dark at speeds faster than 40,000 kilometers an hour. And then, on that day in November 2018, its instruments picked up something unmistakable. The solar wind readings dropped to almost nothing. Cosmic ray levels spiked sharply. The entire character of the magnetic field around it changed. In less than a single day of travel, Voyager 2 crossed from one universe into another. It became only the second human-made object ever to reach interstellar space, following its twin, Voyager 1, which had made the same crossing 6 years earlier in 2012. Now here's where the story gets genuinely fascinating, and here's why Voyager 2's crossing mattered so much more than you might expect. When Voyager 1 crossed the Heliopause back in 2012, it did so with a broken toolkit. Its plasma instrument, the single device built specifically to measure the exact properties of the plasma around it, had stopped working way back in 1980. By the time Voyager 1 reached the edge, that instrument had been silent for 32 years. Scientists still learned a lot from Voyager 1's other instruments, but the most direct, most important measurement, the actual plasma itself, was missing. They had to guess at it indirectly. Voyager 2 was different. Its plasma instrument was still alive, still working after more than 4 decades in the crushing cold and radiation of deep space. Consider what that instrument had already survived by 2018. It had flown past the crushing radiation belts of Jupiter, endured the bitter cold of deep space near Uranus and Neptune, and kept functioning through 4 decades of constant exposure to cosmic rays and solar particles, all while operating on a power source designed for a mission that was only ever expected to last a handful of years. This was almost a miracle of engineering, and it meant that for the very first time in human history, scientists had a spacecraft crossing into interstellar space with a working plasma detector, capturing real direct readings of temperature, density, and speed on both sides of the boundary as the crossing actually happened. That data was pure gold, and what it revealed took scientists an entire year to fully process before they felt ready to publish. To really appreciate why that one working instrument mattered so much, think about what plasma actually tells scientists. Plasma is the 4th state of matter, a hot soup of charged particles that makes up almost everything you can see in space, including the sun itself, the solar wind, and the vast clouds drifting between stars. Measuring plasma directly means measuring the very substance of the boundary itself, not just its side effects. Without a working plasma instrument, scientists studying Voyager 1's crossing in 2012 were essentially reading footprints in the sand instead of watching the actual event happen. They could tell something had crossed, and roughly when, but the fine details, the texture, the temperature, the exact behavior of the plasma at the moment of transition remained frustratingly out of reach. Voyager 2 finally closed that gap 6 years later, delivering the first true, direct, real-time portrait of what it actually feels like, physically, to leave the sun's bubble and enter the space between the stars. The first surprise hit hard. For decades, the leading models predicted that the heliopause would be a slow, gradual transition. Picture 2 rivers slowly merging into one another over a long stretch, blending gently. That's what scientists expected the solar wind and interstellar plasma to do. Instead, Voyager 2's plasma instrument recorded something shockingly abrupt. On November 4th, the spacecraft was still inside the outer layer of the heliosphere. By November 5th, it was fully in interstellar space. Not a slow fade, a hard line. Later analysis measured the width of that transition zone at less than 6/100ths of an astronomical unit, which is an almost impossibly thin boundary when you consider we're talking about distances normally measured in billions of miles. The edge of our entire solar system turned out to be sharper than a single day's travel. If you're enjoying this so far, do me a quick favor and smash that subscribe button, because we're only getting started, and the next few discoveries are even bigger than this one. The second surprise came from temperature. Scientists had long predicted that the interstellar plasma just outside the heliopause would be cold and quiet, a calm, uneventful void. What Voyager 2 actually measured was plasma that was noticeably hotter than expected. Not blazing hot in any dramatic sense, but significantly warmer than 4 decades of careful theoretical work had predicted. The region right outside our solar bubble wasn't the frozen, silent nothing that scientists imagined. It had energy, it had variation. Its properties shifted as the spacecraft moved deeper into it, meaning the space just beyond our sun's reach is far more dynamic. Try picturing it this way. Imagine stepping outside your front door expecting a calm, empty street, and instead finding wind, movement, and shifting temperatures the moment you crossed the threshold. That is essentially what Voyager 2 experienced at the edge of the solar system. The neat, tidy boundary drawn in textbooks turned out to be the entrance to a much livelier, much less predictable region than anyone had modeled. And that single correction, warmer plasma than expected, forced physicists to rethink some of their basic assumptions about how our solar bubble interacts with the wider galaxy surrounding it. The third surprise came from the magnetic field readings. Just inside the heliopause, in that outer shell of the heliosphere, Voyager 2's magnetometer detected something researchers now call a magnetic barrier. This is a region where the magnetic field intensity jumps up sharply, forming a kind of pressure wall between the bulk of the heliosphere and true interstellar space. Voyager 1 had hinted at something like this back in 2012, but Voyager 2 confirmed it with much greater clarity and revealed something crucial about how it works. This magnetic barrier actually helps block incoming cosmic rays, the extremely high energy particles launched across the galaxy, by exploding stars and other violent cosmic events. Those particles are dangerous, and our heliosphere partially shields the inner solar system. The magnetic barrier Voyager 2 detected turns out to be a key part of how that shielding actually functions, and no model built before this crossing had described the mechanism correctly. The fourth discovery came from comparing Voyager 2's crossing with Voyager 1's crossing from 6 years earlier. This comparison turned out to be one of the most important results of the entire mission. The two spacecraft crossed the Heliopause in completely different locations. Voyager 1 crossed in the northern part of the solar system, heading roughly in the direction the Sun travels through the galaxy, toward what scientists call the nose of the heliosphere, the point where the solar wind slams hardest into the interstellar medium. Voyager 2 crossed in the southern hemisphere, heading toward a different region entirely, more like the side, or the flank, of the bubble. If the heliosphere were a perfectly round, symmetrical ball, both crossings should have looked almost identical. They didn't. Voyager 2 found a thinner boundary than Voyager 1 had found. It measured stronger interstellar magnetic fields and different plasma conditions. Both spacecraft crossed at roughly the same distance from the Sun, about 120 astronomical units, which was itself a little surprising, given how different the conditions were at each location. But the character of the boundary itself was clearly different depending on where you crossed it. This tells us something huge. Our heliosphere is not a perfect sphere. It has a shape, stretched and squeezed by the direction our Sun moves through the galaxy. And if the shield around our solar system isn't symmetrical, then the protection it offers against radiation isn't equal in every direction. Some parts of the sky may be more shielded than others. The two Voyager crossings are the only direct measurements taken of this shape. And they're already forcing scientists to redraw the heliosphere as something closer to a windsock caught in a breeze than a smooth, tidy ball. That single shift in thinking changes far more than a diagram in a textbook. It changes how we think about Earth's exposure to radiation. If the shield around us has always been uneven, thicker in some directions and thinner in others, then the story of how much radiation reached us is complex. Two single data points are now quietly rewriting a chapter of Earth's own biological story. The fifth and final major discovery had to do with the interstellar magnetic field itself. For decades, physicists believed the galactic and solar magnetic fields were mostly separate systems, barely interacting with one another. What both Voyager spacecraft found at the boundary told a different story. The two environments are more connected and tangled than predicted. The galactic magnetic field outside turned out to be far stronger than expected, running 2 to 3 times higher than calculated intensity. That stronger outside field pushes back on our heliosphere with much more force than scientists had accounted for. Some estimates suggest the interstellar medium presses against our solar bubble with up to 10 times more pressure than earlier models assumed. That's not a small correction. That pressure is one of the main things determining how big or small our protective bubble actually is. A more compressed heliosphere may offer somewhat weaker shielding to everything living inside it, including us. The Voyager data doesn't prove that our protection is shrinking right now, or that anything dangerous is about to happen. But it does prove that the forces squeezing our shield from outside are much stronger than we thought, and that changes every calculation. All 5 of these discoveries, from the razor-sharp boundary to the powerful outside magnetic pressure, were released together on November 4th, 2019. 5 papers, published on the same day, in the same journal, because the findings were so interconnected that they needed to be seen at once. The reaction from the scientific community wasn't panic. It was something more interesting. It was a genuine, humbling recalibration. One NASA scientist described Voyager 2 as the very first machine to actually experience interstellar space from the inside, calling it a true pathfinder. That word matters. There was no path before this. There were only models and theories built from instruments sitting deep inside the heliosphere. Those models still got the sharpness of the boundary wrong, the temperature wrong, the magnetic strength wrong, and the shape wrong. A single 41-year-old spacecraft held together by 1970s engineering proved all of that. And here's the part that should give you chills. Voyager 2 is not coming home. It never will. But everything it sent back changed the map for good. If this is the kind of real science you love, now's the perfect time to subscribe. We cover discoveries like this every single week. Drop a comment telling me which of these 5 findings shocked you the most. Now let's talk about what's happening right now, today, more than 7 years after that historic crossing. The story didn't end when Voyager 2 broke through the Heliopause. In many ways, that's when the real chapter began. The interstellar medium is not some silent, empty void. It has structure, it has movement. Density and temperature shift constantly. Even more remarkably, scientists have detected pressure waves rippling through this interstellar plasma, triggered by eruptions from our own sun. These eruptions are powerful enough to send shock waves rippling all the way out past the heliopause and into true interstellar space. Voyager 2 has picked up these waves from the outside, proving that our sun's influence doesn't end abruptly at that boundary line. In a strange, beautiful way, the heliosphere seems to breathe. It responds to what our sun is doing internally and to the galaxy outside. Voyager 2 has been quietly recording that breathing pattern from beyond the edge since the very day it crossed. Every single day since November 2018, it has beamed back new readings on plasma density and magnetic field direction. Piece by piece, point by point, it's been building something no one has ever built before, a real map of the space outside our system. Even the most powerful telescopes ever built can only study interstellar space from a distance, filtering through theory and interpretation. Voyager 2 doesn't have to guess. It sits physically inside the environment it studies, feeling the actual particles and magnetic fields. That difference between observing from far away and actually being there is the entire reason this mission remains irreplaceable. Even in an age of incredibly advanced ground-based and space-based telescopes, that map has a deadline. Every year, Voyager 2 loses a small amount of electrical power, roughly 4 watts annually, as its nuclear power source slowly decays. Every year, engineers at NASA's Jet Propulsion Laboratory face harder choices about which instruments to keep running and which to switch off. The plasma instrument that made all of this possible is still operating today, but it simply cannot last forever. In 2023, ground controllers briefly lost contact with Voyager 2 for 14 days after a commanding error. For 2 full weeks, the spacecraft kept collecting data out there in the dark, completely alone, with nobody listening. Engineers eventually managed to re-establish contact using an extremely powerful signal, shouting across the void until something answered back. But those 14 days of readings are simply gone, lost forever, because Voyager 2 only passes through each point in space one time. Whatever the interstellar medium looked like during that silent window will never be known. That small gap is nothing compared to what's coming. One day, likely sometime in the 2030s, Voyager 2 will finally run out of power completely. When that happens, the map stops. Whatever lies farther out in interstellar space will remain a total mystery, because right now, there is no other mission plan to follow. That should make you pause for a second. Right now, today, the only instrument in human history measuring this space is an aging machine. It is older than most of our parents, running on decaying power, sending signals across 11 billion miles that take 20 hours to reach Earth. And when it finally goes silent, we lose our only eyes and ears out there, possibly for decades, possibly for a lifetime. Quick pause, because this next part is exactly why people keep coming back to this channel. Tap subscribe and ring the notification bell. There's an obvious question hanging over all of this. Why isn't there already another spacecraft on the way to replace Voyager 2? The honest answer is that missions like this are brutally difficult to justify, because they take decades to produce valuable data. This is far longer than most funding cycles, most careers, and sometimes most political administrations are willing to commit to. Scientists have proposed an interstellar probe mission designed specifically to reach the Heliopause faster and carry modern instruments. Engineering studies have been done. Concept papers have been written. But, as of now, no such mission has secured full funding. It exists only on paper, waiting for the moment someone decides that continuing this story is worth the investment. That means the gap between Voyager 2 going silent and a replacement reaching the same distance could stretch across decades. Even under the most optimistic timeline, a new probe launched today would need 30 years or more to reach the same distance. In other words, whatever Voyager 2 fails to record before it dies may simply remain unrecorded for the rest of most of our lifetimes. That is the true weight behind every single data point this aging spacecraft still manages to send home. Let's go a little deeper. Why this all actually matters to you, sitting right here on Earth, is that it connects to the reason complex life exists at all. Cosmic rays are constantly streaming through space in every direction. Without our heliosphere acting as a shield, we would be exposed. Scientists believe that heavier cosmic ray exposure could increase mutation rates in living organisms and alter atmospheric chemistry. Our protective bubble isn't just a line on a diagram. It may be one of the quiet reasons life on Earth evolved the way it did. Consider what a world without that shield might have looked like across the billions of years life has existed here. Higher radiation levels could have meant conditions too harsh for fragile early life to survive at all. It's a humbling thought. The very shape of our DNA may have been quietly influenced by a bubble of charged particles most people have never even heard of. So the real question the Voyager data raises is genuinely important. How stable is that protection really, over long stretches of time? The answer depends on the properties of the interstellar region our solar system happens to be passing through right now. If our sun drifts into a denser patch of the galaxy, our heliosphere would get squeezed smaller, offering weaker shielding. Second, the sun's own activity level matters, since more solar wind supports a larger, stronger bubble. Voyager 2 proved the pressure is strong. That means our shield is being squeezed harder than scientists thought, which means it's likely somewhat smaller right now. This isn't a crisis. Our heliosphere is still enormous, still more than capable of protecting the inner solar system today, but it does mean every future calculation about how safe and stable that protection remains now has to be rebuilt using real numbers. Numbers that only existed because one aging spacecraft happened to be in exactly the right place with exactly the right instrument. There's one more detail from this story that deserves real attention because it quietly reveals something poetic about our place in the galaxy. Both Voyager spacecraft crossed the Heliopause at nearly identical distances from the Sun, despite crossing at completely different times. Scientists expected the size of the heliosphere to shift noticeably with the Sun's roughly 11-year activity cycle. They were wrong. The pressure coming from interstellar space is steady and strong enough that it barely matters what our Sun is doing internally. The galaxy, in a sense, holds the line. Our Sun pushes outward with everything it has, and the galaxy pushes back just as consistently. There's something strangely comforting about that image, our star straining against the pressure of the entire galaxy, managing to hold steady. It also means the danger, if it ever comes, won't arrive because our Sun suddenly grows weak or quiet. It will be the environment. Our Sun orbits the center of the galaxy every 230 million years, drifting through vastly different neighborhoods of gas and dust. Right now, we happen to be passing through a relatively calm patch of the galaxy, sometimes called the local bubble. That calm patch is one of the quiet reasons our heliosphere has remained as stable as it has throughout recorded human history. Whether that calm continues is a question no model can currently answer with full confidence. It's a question only direct measurements can solve. That relationship between our Sun and the vast galaxy was described incorrectly for decades, right up until 2018. And that spacecraft is still out there right now, farther from Earth than it was yesterday, its power a little weaker than last year. But it is still transmitting, still measuring, still doing exactly the job it was built for before most current scientists were even born. Think about what it means that a piece of 1970s engineering is currently our only direct source of truth about the space between stars. No other supercomputer or telescope can do what Voyager 2 is doing right now, simply because none of them are actually out there. Being there, physically present in that specific patch of interstellar space, turned out to matter more than any indirect observation. Theories are only ever theories until something crosses the line and tells you what's actually on the other side. That's the real lesson. It's a reminder of how much of what we consider settled science is really our best available guess, waiting to be tested against reality. For decades, the smartest people on the planet built increasingly detailed models, and still, direct measurement proved them wrong. That's not a failure of science. That is exactly how science is supposed to work. Build the best model you can, then go test it. It's worth remembering how much confidence surrounded the old heliosphere models before 2018. They were backed by decades of math. Entire careers were built refining those models. And still, when actual measurements finally arrived, several predictions turned out to be wrong. That's not an embarrassment. If anything, it's a testament to how honestly they approached the problem once the new data arrived. Instead, 5 teams sat down, studied the readings carefully for an entire year, and rebuilt their understanding from the ground up. That kind of intellectual honesty is rarer and more valuable than most people realize, whether in space physics or everyday life. There's also something worth appreciating about the sheer patience this discovery required. No one person could take full credit. Many of the engineers who originally built and launched Voyager 2 back in 1977 had long since retired by the time it reached the edge. The scientists who analyzed the data in 2019 inherited a project older than their own careers, built by a previous generation of dreamers. That kind of long-term thinking, building for a payoff that might not arrive for 40 years, is almost unheard of in our modern world. Voyager 2 is proof that it can still work and that it's still worth doing. Somewhere out there, a machine is drifting silently. It carries a golden record with sounds and images of Earth, sent out as a message to anyone or anything that might one day find it. It has already outlived its original mission by decades. It has already rewritten our understanding of where our solar system truly ends. And it is still working, still listening, still speaking back to us across a distance so vast that messages take nearly a full day to arrive. Try to picture the actual scale of that distance for a moment. Light itself takes almost 20 hours to cross that gap. When engineers at Mission Control send a command, they wait nearly a full day just to find out if it worked. That is true persistence. When the spacecraft sends a reading, that data has already been traveling for the better part of a day before reaching our giant antennas. We are, in every meaningful sense, receiving messages from yesterday, sent by a machine built the better part of a century ago. And yet, because of it, we understand our own cosmic neighborhood more clearly today than at any point in human history. One day, it will stop. Its power will run out, its instruments will fall silent, and it will keep drifting forever long after everyone alive today is gone. Scientists estimate the golden record itself could remain intact and readable for well over 1 billion years, a silent legacy of humanity. In some strange, quiet way, Voyager 2 has already outlived the purpose we gave it, and is now simply continuing faithfully. But for now, right now, while you're watching this, it is still awake, still reaching back across 11 billion miles to tell us the news. Every discovery we walked through today exists because one aging spacecraft refused to stop working against all the odds. That is the real story here. Not just what Voyager 2 found, but the fact that it was still capable of finding anything at all. If this story moved you, make sure you're subscribed. Tell me in the comments which part of this crossing surprised you the most. If you know someone who still believes the solar system just quietly fades away into nothing, send them this video right now. The truth is a lot more interesting than that. Thanks for watching, and I'll see you in the next one.